Hello everyone. Thanks to everyone for watching this video. My name is Qi Dao. I am an architect and engineer. Today's video is titled Serviceability Requirements, and it is going to provide you a broad overview of the serviceability limit states and also the calculation of deflection and cracking. I am going to give you an overview of what I am covering today's video. First at all, we will have a look at some fundamentals of the serviceability limit states, then move on to the calculation of deflection and cracking, then wrap up with conclusions. For reinforced concrete structures, the serviceability limit states are often satisfied by observing empirical rules, which affect the detailing only. In some circumstances, however, it may be desired to estimate the behavior of a member under working conditions, and mathematical methods of estimating deformations and cracking must be used. Where the foundations of a structure are in contact with the ground, the pressures developed will influence the amount of settlement that is likely to occur. To ensure that these movements are limited to acceptable values and are similar throughout the structure, the sizes of the foundations necessary are based on the service loads for the structure. In this video, we will focus on the deflection and cracking for the reinforced concrete structures. First, we will introduce the calculation of deflection. The general requirement is that neither the efficiency nor the appearance of a structure is harmed by the deflections that will occur during its life. Thus, deflection must be considered at various stages. The limitations necessary to satisfy the requirements will vary considerably according to the nature of the structure and its loadings. For reinforced concrete, the final deflection of a beam, slab, or cantilever should not exceed span over 250. That part of the deflection which takes place after the application of finishes or fixing of partitions should not exceed span over 500 to avoid damage to fixtures and fittings. The code suggests that deflections should be calculated under the action of the quasi-permanent load combination, assuming this loading to be of long-term duration. Hence, the total loading to be taken in the calculation will be the permanent load plus a proportion of the variable load, which will typically be 30% of the variable load for office-type construction. This is a reasonable assumption as deflection will be affected by long-term effects such as concrete creep, while not all of the variable load is likely to be long-term and hence will not contribute to the creep effect. Curvature under the action of the quasi-permanent load should be calculated based on both the cracked and uncracked sections. An estimate of an average value of curvature can then be obtained using this formula, where 1/r is average curvature, 1/r UC, and 1/r CR are values of curvature calculated for the uncracked case and cracked case respectively. C is coefficient given by 1 minus beta times sigma SR over sigma S square, allowing for tension stiffening. Beta is load duration factor, 1 for a single short-term load, 0.5 for sustained loads or cyclic loading. Sigma S is stress in the tension steel for the cracked concrete section. Sigma SR is stress in the tension steel calculated on the basis of a cracked section under the loading that will just cause cracking at the section being considered. Appropriate values of concrete tensile strength to be used in the calculation of sigma ST can be obtained from this table. In calculating C, the ratio sigma SR over sigma S can more conveniently be replaced by MCR over M, where MCR is the moment that will just cause cracking of the section, and M is the design moment for the calculation of curvature and deflection. The assumed elastic strain and stress distribution for an uncracked section is shown in this figure. For a given moment m, and from elastic bending theory, the curvature of the section 1/r UC is given by this equation, where EC effective is the effective elastic modulus of the concrete allowing for creep effects, and IUC is the second moment of area of the uncracked concrete section. The assumed elastic strain and stress distribution for a cracked section is shown in this figure. Moments of area can be taken to establish the neutral axis depth directly. The second moment of area of the cracked section can then be determined by taking moments of area about the neutral axis as this equation, where alpha E is the modular ratio equal to the ratio of the elastic modulus of the reinforcement to that of the concrete. For a given moment m, and from elastic bending theory, the curvature of the cracked section 1/r CR is therefore given by this equation. The deflection of the beam or slab can be calculated from the total curvature using elastic bending theory, which for small deflections is based on this expression, where mx is the bending moment at a section distance x from the origin, as shown in this figure. For small deflections, the term d squared y over dx squared approximately equals the curvature, which is the reciprocal of the radius of curvature. Double integration of this equation will yield an expression for deflection. This may be illustrated by considering the case of a pin-ended beam subject to constant m throughout its length. So that mx equal to m, we can derive this equation. If the slope is 0 at the midspan, where x equal to half of L, then we obtain c equal to minus half of m times L. Integrating again gives this equation. At support A, when x equal to 0, y equal to 0. Hence, we obtain d equal to 0. Thus, we obtain this y equation at any section. The maximum deflection in this case will occur at midspan, where x equal to half of L, in which case y max equal to minus m over ei times L squared over 8. But since at any uncracked section, m over ei equal to 1 over r, so that the maximum deflection may be expressed as this y max equation. In general, the bending moment distribution along a member will not be constant, but will be a function of x. However, the basic form of the result will be the same, and the deflection may be expressed as this equation, where k is a constant, the value of which depends on the distribution of bending moments in the member. L is the effective span, L over Rb is the midspan curvature for beams, or the support curvature for cantilevers. Typical values of k are given in this table for various common shapes of bending moment diagrams. If the loading is complex, then a value of k must be estimated for the complete load, since summing deflections of simpler components will yield incorrect results. Next, we will introduce the calculation of cracking. Members subject to bending generally exhibit a series of distributed flexural cracks, even at working loads. These cracks are unabrasive and harmless unless the width becomes excessive, in which case appearance and durability suffer, as the reinforcement is exposed to corrosion. If the behavior of the member in this figure is examined, it can be seen that the overall extension per unit length at the depth y below the neutral axis is given by this equation, where epsilon s is the average strain in the main reinforcement over the length considered, and may be assumed to be equal to sigma s over es, where sigma s is the steel stress at the cracked sections. Epsilon 1 is the strain at level y, which by definition is the extension over the unit length of the member. Hence, assuming any tensile strain of concrete between cracks is small, since full bond is never developed, the total width of all cracks over this unit length will equate to the extension per unit length. That is this equation, where sigma w equal to the sum of all crack widths at level y. The actual width of individual cracks will depend on the number of cracks in this unit length, the average being given by unit length over average spacing SRM. Thus, we have this equation. However, the designer is concerned with the maximum crack width, which has an acceptably low probability of being exceeded. For design purposes, the design maximum crack width, WK, can be based on the maximum spacing, SRmax. Hence, the design crack width at any level defined by y in a member will thus be given by this equation. The expression for the design crack width given in Eurocode 2 is of the above form and is given as this equation, where WK is the design crack width, SRmax is the maximum crack spacing, epsilon SM is the mean strength in the reinforcement, allowing for the effects of tension stiffening of the concrete. Epsilon cm is the mean strength in the concrete between cracks. The mean strength epsilon sm will be less than the apparent value epsilon 1, and epsilon sm minus epsilon cm is given by this expression, where sigma s is the stress in the tension steel calculated using the cracked concrete section. Kt is a factor that accounts for the duration of loading, 0.6 for short-term load, 0.4 for long-term load. The maximum crack spacing, SRmax, is given by the empirical formula as this equation, where phi is the bar size in millimeter, or an average bar size where a mixture of different sizes have been used, and C is the cover to the longitudinal reinforcement. K1 is a coefficient accounting for the bond properties of the reinforcement, 0.8 for high bond, 1.6 for plain bars, and K2 is a coefficient accounting for the nature of the strength distribution, which for cracking due to fracture can be taken as 0.5. Rho P effective is the effective reinforcement ratio, AS over AC effective, where AS is the area of reinforcement within an effective tension area of concrete, AC effective, as shown in this figure. The effective tension area is that area of the concrete cross-section, which will crack due to the tension developed in bending. This is the cracking which will be controlled by the presence of an appropriate type, amount, and the distribution of reinforcement. From conclusions, what we learned: the deflection in reinforced concrete, usually measured as a linear displacement transverse to a reference line or axis. It is an important serviceability consideration in the structural design of concrete buildings. The actual width of cracks in a reinforced concrete structure will vary between wide limits and cannot be precisely estimated. Thus, the limiting requirement to be satisfied is that the probability of the maximum width exceeding a satisfactory value is small. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.